Right, in this video, we're going to look at reactions of alkenes, okay? And it's going to be basically the subject of chapter 6, and this is going to be continuing over about 3 videos. Okay, the first reaction that we're going to talk about is called catalytic hydrogenation, okay? And this is where we just take the elements of H2, a hydrogen molecule, and add those 2 hydrogens across a double bond to convert an alkene into an alkane. Okay? Notice that in this process, we have taken the alkene pi bond, and it's gone now. It's been replaced with 2 equivalent CH sigma bonds. And this is a common feature of most of the reactions in chapter 6, of most of these alkene addition reactions. This reaction requires a catalyst, usually platinum or palladium in most of the cases that we'll see. Sometimes you'll see nickel or rhodium, and if you look in the literature using a proper search engine like, in the American Chemical Society, we use SciFinder. If you look at all the metals that have successfully been used in catalytic hydrogenation, you'd probably find that virtually every transition metal has been successfully used in this process by someone. Okay. I'm not going to go through the mechanism of this process in detail. Let me just tell you what the role of the metal is. It's to break the HH bond and to form a complex with the alkene pi bond. Okay? These 2 things are what is occurring to metal. It basically brings all of them together. The process is somewhat complex. You would really need to understand the reactions of organotransition metal compounds to fully understand the mechanism for the hydrogenation reaction. Okay, hydrogenation, we say it's an exothermic reaction. Heat is produced. Okay, the amount of heat that we're producing is, we're just going to call it the heat of hydrogenation, abbreviated this way. And this is just the amount of heat that we get out of the system by doing a hydrogenation reaction. Alkene hydrogenation reaction is always exothermic. Okay? Well, we can look at, or the heat of hydrogenation can tell us a lot about the relative stability of an alkene group. Okay? And if we assume that the alkanes that we're producing are relatively of equal stability, what we can say is that the heat of hydrogenation can directly compare with the alkene stability. Okay, so higher heat of hydrogenation translates to a less stable alkene. Okay, so in the past we were using heat of combustion to determine alkene stability, but when we do that we're limited by the fact that we have to have isomeric alkenes. Now we don't have to have that limitation anymore. We're just looking at how stable is the alkene where it's located in that molecule. And what we see here is that heat of hydrogenation follows exactly the same trend as we noticed for heat of combustion. The most, or the least stable type of alkene is the monosubstituted alkene. It has the highest heat of hydrogenation. Cis 1,2 disubstituted is higher than trans 1,2 disubstituted, and as you substitute the double bond even more, the heat of hydrogenation goes down. Okay. All right, so hydrogenation is a reaction you've probably heard of. It's heavily involved in nutrition science, so let's just look at that. We'll look at that in a second. Let me just say some other things about it first. Okay. Hydrogenation is what we call a syn addition. Both of the hydrogen atoms add to the same face of the alkene. It's a little hard to tell it when you're adding hydrogens because there's hydrogens already there. So we'll just look at the reaction from adding heavy hydrogen or deuterium. So if you take cyclohexene, deuterium, and palladium on carbon, a common hydrogenation catalyst, what you find is that you make the compound where the two deuteriums that you added to the system have been added in a cis fashion. We call this a syn addition, addition to the same face of the alkene. And all of the additions that we do in this chapter, we're going to classify them as either syn additions, anti-additions where they add to the opposite face, or random additions where there's no control over the stereochemistry. Okay, here's another issue here. This occurs when we have stereochemistry, or we have substituents on our alkene that differentiate one face from the other. If we were to take this compound and treat it with hydrogen and platinum, we could isolate two different compounds. We could produce the cis compound or the trans compound, but this reaction produces a huge excess of the cis compound. And why is that the case? Okay, so let's just divide this alkene into two faces. The top face up here, which is on the same side as the ethyl group, and the bottom face down here, which is on the same side as a hydrogen. Okay, an ethyl is much larger than a hydrogen, so we say that this face is harder to access. This is the, we'll call it the hindered side. Okay, if any reagent approaches from this direction, it has to get by the ethyl group. If it comes from this side, however, it's much easier. All right, so when platinum makes a complex of the alkene and breaks the HH bonds, we have a species like this. And the key thing here to note is that it's on this face. It's on the face opposite the ethyl group. So all the hydrogens add to the bottom face. The net result is that the original hydrogen that you had and the new hydrogen that you have are both cis to each other, because that's where they have to be, because of this relationship right here. And this establishes that we're going to get the cis stereochemistry as the major product. Okay, let's look at a problem here. Predict in each case the major product of each reaction. Okay, you should do this yourself. Pause the video and try to predict it. I'll go through it right now. Okay, in this one, we have to consider this cyclohexane's really a chair, but that's not really going to be the issue, regardless of the conformation of cyclohexene. Okay, and this is, sorry, a CH2 group. We're going to have the hydrogens on this side. Okay, let me see if I can draw this a little better. And the six-membered ring down here. And what you see here is that the side that's on the same side as the six-membered ring is kind of hindered. Nothing wants to come from this direction, right? So we want to come from the same direction as the hydrogens that are depicted here. So we're going to add our new reagent, cis to these hydrogens, and this is the product that we would predict that we would get from this one. Okay, in the second case, it's a syn addition, so this means we're using deuterium, so this means that the two deuteriums have to come from the same face. Don't forget that from the bond line diagram that there's still a hydrogen here. Okay, and when we add the two deuteriums, they have to add from the same face of the alkene, and this is the product that we get. We have to get the product where the deuteriums are cis to each other. Okay, all right, so here's that product. Okay, now for some nutrition terms. You heard the term hydrogenation for a large part of your life, right? People are talking about margarine being bad for you because it's partially hydrogenated vegetable oil. Okay, what's the deal there? Why would people want to hydrogenate vegetable oil to begin with? Okay, right, so this is a fat molecule. This is the general structure of it. It is a group here that we're just going to call an ester, and it has a long hydrocarbon piece to it. Okay, so butter, which is predominantly an animal fat, and most animal-derived fats are heavy in what we call saturated fat. This means that they are, this alkyl chain here is a saturated, no alkene group. Chain. Okay. All right. But a lot of the sources of fats that come from plants have alkene groups in them, and all of these alkene groups are, or almost all of them that are produced in nature, have the cis double bond geometry. Okay, so a saturated fat is a solid. An unsaturated fat, one that has a double bond in it, is typically a liquid. An unsaturated fat is also a little bit less stable in the environment because after several months in the air, you can make this group here called a hydroperoxide. And this is responsible for the rancidity, okay, or the stale taste of fat that's been around too long, okay. And so the food manufacturers said, okay, we can provide something that's going to be more environmentally stable by getting rid of the double bonds. So that's one reason to to hydrogenate vegetable oil. The other other reason is to turn your liquid into a solid, okay? So if you want to make synthetic butter from vegetable oil, you're going to have to turn it into a solid, and one of the things you can do is hydrogenate it, okay? Now, completely saturated fat is has a kind of a high boiling point. It's what we call hard as a brick. Okay, so butter has just enough unsaturated fat in it to that it isn't quite as hard, not very hard. So what the food manufacturers have had to do is to what we call partially hydrogenate it, not hydrogenate it to completion, but hydrogenate it partially. And when you subject an alkene to a hydrogenation catalyst without hydrogen, it can cause the cis configuration to isomerize to the trans. Okay, and trans doesn't really occur very often in nature. So when partially hydrogenated vegetable oil or margarine was introduced, it, was completely unnatural because you took the naturally occurring cis fats and you turned them into trans fats. Okay, so this is why you can't buy margarine at the health food store. Or at the organic food store, health food store, it's because it's a natural synthetic compound. Okay, so this has taken a lot of criticism. Some of the things that you can do if you see like the natural margarines, what they do is they mix the completely saturated fat, which has its problems, but it's not as bad as trans fats, with the naturally occurring cis fat that's never been hydrogenated, and that will produce something with the right consistency and avoid the trans fat. Okay, let's look at another issue. You may wonder what's an omega-3 fatty acid. This is also an alkene term. This is defining the alkene position. So if you ever hear these fancy term omega-3s, it means that if you start at the end of the chain and you get to the third carbon, it's an alkene. That's an omega-3 fatty acid. And that's not quite as common in nature. There's not that many sources that produce it, mostly fish and walnuts and I guess flaxseed and a few things like that produce the omega-3 fatty acids, so it's not quite as common as other double bond locations. Okay, here's another addition reaction we're going to look at. This is the addition of hydrohalic acids, HX addition. So if we take HX, where X is Cl, Br, or I, what we find is that we'll add hydrogen to one of the alkene carbons and the X group to the other alkene carbon. This HX has to be usually free of water. It's usually the gas that we're looking at. Water actually weakens it considerably. Okay, we can't use HF because it's not a strong acid. Okay, and this is another example where we're replacing the CC pi bond with the sigma bonds to H and X. Alright, if our alkene is unsymmetrical, we're going to find that we have a very selective reaction. So this simple unsymmetrical alkene here, I guess 1-pentene, reacts with HBr. There are two hypothetical products. We could put bromine at the 2 position or bromine at the 1 position, and the hydrogen here is just going to join the other hydrogens that are already there, make a methyl group here, make a CH2 group here. Well, this reaction is very selective. It produces only this. The selectivity is absolute. There's none of the other product produced at all. Okay, so let's look at the mechanism. The mechanism is a carbocation mechanism. What we see here is that we're adding the H plus of the HBr is being attacked by the alkene. Okay, and there are two hypothetical products from this initial attack: the secondary carbocation or the primary carbocation. We've known for a long time that the primary carbocation is more stable, so it's going to form the secondary carbocation. And if it ever did form the carbocation, of course, this would rearrange to that anyway. Okay? Alright, so when the bromine attacks, it's just going to attack the position of the carbocation right there. And that's why we end up with that product. Okay, so it results from a carbocation intermediate and a preference in this reaction for forming the more stable carbocation. Okay, the simple reaction here is going to be our first example of something called Markovnikov's rule. This chemist gets a lot of play. This rule, he made a lot of early observation and referred to this orientation as Markovnikov orientation. It's where the X goes to the more substituted carbon and the H group goes to the less substituted carbon. Sometimes people refer to Markovnikov's rule as the rich get richer and the poor don't get poorer. They just stay poor. Okay, all right. And then this is referred to as Markovnikov orientation. This is where the X or the nucleophile goes to the more substituted carbon and the H or the electrophile goes to the less substituted carbon. The opposite orientation is referred to has the anti-Markovnikov orientation. Okay, let's look at predicting the products of these reactions here. Okay, again, you should pause the video, predict the products, and then see if you got it right. HBr adding to this alkene. All right, so when this happens, we have a choice, of course, to add to this face to make the tertiary, or we can add to the other side to make secondary. Of course, it's not going to make this when it could make the other one, and bromine is going to come in later. Add right there, and that's the product that we predict. Okay, in the second one here, we're adding exactly 1 mole of HI. Here it's important to remember that alkyl groups are electron donating. Okay, so this means that the more alkyl groups that you have on your alkene, the more reactive it's going to be, the more basic those lone pairs are. So we have a tri-substituted and a mono-substituted alkene. We're going to see another way of looking at this in a second too. We're going to react preferentially at the more substituted alkene group because that's the one that's more electron rich. Okay, this is the product, and when we look at the best carbocation that you could get from attacking the mono-substituted is a secondary carbocation right here, whereas the best carbocation you could get from attacking the tertiary or the tri-substituted olefin is this tertiary carbocation right here. And this carbocation would be much more stable than this carbocation. And the initial alkene group is also more reactive. We'll discuss that when we finish talking about electrophilic additions, that how electron donating groups affect the relative reactivity of alkenes. Okay. The next reaction, and the last one we're going to look at in this video, it's actually several reactions we're going to look at, but they're all classified as alkene hydrogenation. Okay, we can do Markovnikov orientation, where we add water to the across the alkene group. And here we have the Markovnikov orientation, where we took the more substituted carbon and put the OH there, and the hydrogen added to the other carbon and joined the two hydrogens that were already there to make a CH3 group. Okay. There are 3 ways to do this. The first 2 aren't perfect, and the last one is chemically perfect, but an environmental hazard. Okay, so let's look at the 3 methods. Okay. All right. What we can do is just treat it with aqueous H2SO4. This sometimes works. This is the reverse reaction of acid catalyzed alcohol dehydration that you saw in the previous chapter. This reaction is unreliable because most of the time the reaction goes the wrong direction. Alcohol dehydration is the usually in most cases it's the more facile process. It's hard to generate conditions that favor addition of the water across the alkene. Okay, we can treat it with sulfuric acid. We'll have a hydrosulfate intermediate, and then break that apart with water and heat. This is a little more successful than the above reaction, but it's still got a problem with equilibrium issues. Basically, it produces sulfuric acid as a byproduct when there's heat around, and that's a recipe for a dehydration product as well. If you truly want to hydrate an alkene in high yield, you'll use condition C, which involves mercuric acetate in water or wet solvent followed by a treatment with something called sodium borohydride. This is very reliable, but there are serious issues with toxicity, and you don't want to run this on large scale because it's an environmental hazard. This reaction's in your textbook, but it's presented after the problems in Chapter 6. Okay, you can also do the anti-Markovnikov addition of water. Okay, this is not accomplished with water itself. It's accomplished with boron reagents. So we'll talk about this in a few minutes. This is hydroboration-oxidation. Okay, so let's look at method B there. We're not going to go through method A because it's not reliable and it's just the reverse of a reaction we've already studied in some level of detail. All right, so if you treat an alkene with sulfuric acid, and this is sulfuric acid neat, not aqueous sulfuric acid, you're going to get this compound known as a sulfate ester, and this goes via Markovnikov addition. We protonate the alkene to get the better carbocation. The bisulfate anion comes in, adds here, and this produces the product. Okay. Once you have this, you can now treat it with water and heat. This will form the alcohol and produce sulfuric acid as a byproduct. Okay. Because you're making sulfuric acid and an alcohol in heat, sometimes this is going to lead to dehydration as a side reaction. All right, the most reliable way is to use mercuric acetate. Here's what's happening with mercuric acetate. Acetate, if you haven't seen that before, is the conjugate base of acetic acid right there, commonly abbreviated OAC. Okay, so what's first going to happen is we're going to reversibly dissociate or ionize mercuric acetate. This species here is going to be attacked by the alkene. Okay, it's going to make a complex. We can draw this resonance form for the complex as well. This is called the mercuronium ion. It's in equilibrium with a secondary carbocation. It's hypothetically in equilibrium with a primary carbocation as well, but this process is less likely, so let's just disregard that. Okay, so once we open this way, water comes in and attacks. Okay, we're going to remove the extra proton from water with the acetate anion. This is going to make this an acetic acid. You could, if you wanted to, isolate this. This could be isolated. However, the world has limited demands for compounds with mercury in it. So what happens here is this is treated with sodium borohydride, and this basically reduces the carbon-mercury bond to a carbon-hydrogen bond. Okay, you have two CH bonds in the starting material, 3 CH bonds in the product, and mercury metal is a byproduct. Okay, and this is very reliable, but again, it involves dealing with some rather toxic things, so people would not want to do this reaction unless they truly wanted the alcohol in high yield. Okay. Let's look at the opposite way. This is going to involve use of the element boron. BH3, we've already discussed it. It's the simplest molecule we use to illustrate sp2 hybridization, and remember that it has an empty p orbital which can act as a Lewis acid or an electrophile. Okay, BH3 is an unstable compound. It actually dimerizes to form this compound B2H6, which is a much more stable compound, but B2H6 is in equilibrium with two BH3 molecules. Another source of BH3 that's commonly used and is commercially available is something called BH3-THF. This ether, or this compound right here, is called tetrahydrofuran, and it forms a Lewis acid, Lewis base adduct with BH3 that readily releases BH3. So we could regard both of these two compounds as handy sources of BH3. Okay, so if we treat a molecule, an alkene, with B2H6 or BH3-THF, followed by basic hydrogen peroxide, we'll get the alcohol with the anti-Markovnikov orientation. The hydrogen that you've added comes from here, and this hydrogen over here basically comes somewhere from one of these hydrogens, or the hydrogen in the water. Okay, if we take a cyclic alkene, what we find here is that we get actually a pretty good control of stereochemistry as well. What we find is that the hydrogen that we're adding and the OH group end up on the same face of the molecule. Thus we describe this as being a syn addition. Okay, and the stoichiometry of these reactions are important too. It only requires 2/3 of a mole of B2H6, or actually 1/3 of a mole of BH3, or you can say 1/3 of a mole of BH3-THF would suffice for bringing this reaction to completion. Okay, here's the mechanism. It's kind of elaborate. I don't think I would ask to repeat this mechanism on the exam, but let's just look at it and see what goes on here. One of the differences of BH3 versus every other hydrogen source that you've seen is that BH3 is a source of hydrogen with a partial minus charge, and we call this hydrogen with a partial minus a hydride, okay, as opposed to a proton, which has H plus character. Okay, so this empty p orbital at boron is the electrophile. We can imagine that our arrows are going this way. We could produce boron here to make the more stable carbocation, and this extra hydride is just going to add there to produce this. Okay, and this regiochemistry that you see here would make sense, right? If boron is adding first to make the carbocation, boron should be at the end. Most people think, however, that this is a concerted addition where hydrogen and boron are basically adding at the same time. I just show this here because this helps you understand why boron ends up there. And because it's adding in this fashion, the boron and the hydrogen are adding to the same face of the alkene. Okay, notice that here we still have two active BH bonds, right? One here, one here. These remaining BH bonds can do exactly what this first BH bond did, react with two more alkene units, and this is going to make a species that's called a trialkyl borane. You could isolate this if you want to, and actually some recent Nobel Prize winning chemistry has actually involved uses of the trialkyl boranes, but we'll not discuss that for now. Let's just look at how we can convert the trialkyl borane into an alcohol. All right, this sits there waiting for someone to add some basic hydrogen peroxide. The hydrogen peroxide, remember boron has got an empty p orbital right here, so we can add here. This is going to make an anion at boron. This is now going to migrate to oxygen, cleaving the OO bond. An OO bond is actually a weak bond, and this is going to now give us a CO bond and instead of a CV bond. Okay. Eventually, all of the carbon-boron bonds are going to do this, and these basic conditions are going to cleave the oxygen-boron bond as well, and we're going to end up with the alcohol and sodium borate. Okay, what happens if we have a flat molecule? Okay, so I'm going to just illustrate it with the other example here. All right, because they're adding at the same time, this means that hydrogen and boron are going to the same face. And remember that we're adding 3 of them, so there's going to be 3 of these attached to a single boron. Now we're going to add the basic hydrogen peroxide. We're going to get this. This is not a stable compound. It's merely an intermediate under these reaction conditions. And because this migration process, CO bond formation, is occurring what we say with retention of configuration, the CO bond exists where the BO bond used to be. This sets the stereochemistry, and the cleavage with base gives us the final product that you see here. Okay? The net result is that the elements of water, H2O, the new parts, come or add to the same face, and that's where your syn addition comes from. And the regiochemistry is the same as in the other example. You get boron and oxygen to the less substituted carbon, and hydrogen at the more substituted carbon, the anti-Markovnikov orientation. Okay, we're going to end this video with a problem. You should pause it and do it, but let's just think about what we get here. Predict all of the likely products, including stereoisomers, that you would get from each reaction. Okay, so the first one is a Markovnikov addition. So we're going to add OH here and H there. Our product is going to be both of these 2 compounds. Okay, we could get either stereoisomer. There's no control over which face that we're going to add to. We're going to explore more stereochemical issues like this in the next chapter. All right, this next one, it's going to be opposite. OH is going to end up at that carbon. Hydrogen is going to end up at this one. Hydrogen and OH that you're adding have to add to the same face, but the methyl that you see out here, of course, is not involved in the reaction at all. So that's going to stay the same. All right, so these are the 2 products that you should get. Note that both of them have the same feature, that hydrogen and OH added to the same face. The new hydrogen and the OH group added to the same face. And there's 2 orientations relative to the methyl group that was already in the molecule. So these are the 2 hypothetical products that you could form here. Okay, so we're going to end this video and we're going to look at some more electrophilic additions to alkene groups in the next one.